as we go over this. All right. So we've got this ramp over on the right, and there's at the top, a sphere and a cylinder, solid cylinder, and a hoop, and a frictionless box. And they all have identical masses, which means that whatever that hoop is made out of, it's pretty dense. And they all have the same heights, or in the case of the round things, the diameter of all these round things is the same as the height of the box. Number 1 asks you to rank the objects according to their arrival times at the bottom of the ramp. And you could assume that it's a smooth rubber ramp, so it's a grippy surface that nothing's going to slip on except for the box, because the box is frictionless. Think about that for a moment. It may help you to know that the other class didn't do very well. Their predictions were pretty far off, but that's good, because that means that this is worth me teaching you, or at least worth us talking about. The second question, which I'm going to interrupt you a little bit with, is maybe worth mentioning before you do the first one, because it actually, the reason I put it there is because it's a good way of thinking about the end result. So number 2 says, suppose that the bottom end of the ramp is frictionless. So after the objects get to the ground, there's no friction, and then they hit a vertical frictionless wall. And what would happen then? What I mean by that is, here's the ramp, here's the ground, here's the wall. So all the objects come down the ramp, which does have friction, except for the box. And then they get to the bottom, and if we're talking about the sphere, it's going to roll here, and then it's going to hit the wall. And it can't, it's just going to stop there. Let's assume that it stops. It doesn't bounce back. So I think the question there is, what motions, if any, would continue after impact? So if the ball doesn't actually bounce, even if it did bounce back, what motions would continue once these things hit the frictionless wall? Both the wall and the floor would be frictionless at this point. So let me go back to here again. Give you a little more time to think about it. It's really not important. You don't need to get it right. They all got it wrong. All right, so what I want to know from you is which one do you think would... You're supposed to rank these, so we could do let's do the fastest one first. How many people think that I'll go from right to left, that the box, the frictionless box, is going to be the fastest one to the bottom? Raise your hand. All right, no hands for that one. How about the hoop, the thin hoop? How many people think it'll get to the bottom fastest? All right, how about the cylinder? Well, either everybody's hesitant to guess, or you're not connected, or something, or everybody thinks it's going to be the sphere. How many people think the sphere will get to the bottom first? Oh, good. I'm glad people actually have some answers here. Well, I'm going to tell you that it's not the sphere. However, the sphere would be the second fastest to the bottom. The fastest one would be the box, the frictionless box. If there were friction, it'd be a very different answer. But if the box didn't have any friction, it's going to get to the bottom the fastest. And the reason for that has to do with number 2. So let me go back to this picture and talk about what's happening a little bit. So if we just imagine what's happening with the sphere, which is actually pretty fast, it's motionless, and then because there's friction right here, the friction between the sphere and the ground, that static friction, holds the bottom in place, which causes the top of the sphere to kind of roll over it. And that's how rolling works. As it's going down, there's always a little friction right here, and the tilt causes the top to roll over the bottom. So this rolls and rolls and rolls. Now when the sphere gets to here, it's going really fast, it's rolling along, and then it hits the wall. And let's just say it doesn't go any further. It just stops right there. Does it stop spinning?
It keeps spinning.
It would keep spinning, exactly. So the trick here is that you could look at it two different ways. There's one way to look at this is there's a new kind of kinetic energy. What we've been doing so far in this class is saying things like, this has a certain potential energy which is equal to mgh. So when it's up here, it's got potential energy, and when it gets to the bottom, it's got kinetic energy, and the kinetic energy is 1/2 mv squared. And if we were to calculate that kinetic energy, we would calculate it based on how fast the ball is moving left to right. This would be the v right here. But once that motion stops, once the ball stops there, it's still spinning, so it still has kinetic energy. So what happens with any rolling object is that this potential energy that it has in the beginning, I'll just write PE initial equals KE translational final plus KE rotational final. So with a rolling object, this energy is getting turned into two different kinds of kinetic energy. The translational energy, which is carrying it in a line down the hill, which determines how fast it's going to go. But then also the rotational energy, which even after it stops, as long as there's no friction, it'll keep spinning around here. So in the case of the box, the box is up here, it doesn't roll at all. So all of its initial potential energy, mgh, gets turned into the translational kinetic energy. And tomorrow we'll go over this, but the formula for this and this is 1/2 mv squared, as we've learned before. And the formula for this is 1/2 I omega squared. And I is the rotational equivalent of mass, and I has to do with how hard it is to start something rotating. Which brings me to the second way to look at this. Of all the objects, I'll just tell you. Actually, I don't want to tell you the answer first. I'll explain this, and then we can figure out the answer. So if you have on a ramp a sphere, which is going to look a lot like a cylinder, or maybe I'll draw a perspective of this. This is the cylinder. And then there's a thin hoop, which I'm going to have trouble drawing this one. Just draw it like that. It's kind of like a hollowed out cylinder. So in order to start these rolling, like I was saying, there's friction at the bottom. So that bottom point where these are all touching the surface, that's stuck. And gravity basically starts to pull the center of mass this way. So there's a force applied, and it's the same force for all three. This one is the hardest to roll because in order to roll this has got all this mass on the outside. If you think about all the mass being accumulated up here, if I need to start rolling this, these little bits of mass, they're going to have to move through a big distance since they're a long way from there, and they're actually a long way from the center of rotation. Something like a sphere, which is fat in the middle and has less mass toward the outsides, that's going to be easier to roll because most of the mass is right around the axis, and it doesn't have to move in very big circles in order for this to roll. And then the cylinder is kind of in the middle. So to make a long story short, when you have an axis of rotation, let's say that's the axis, if you wanted to design an object that would be very easy to to roll, it would be something like, I don't know, just draw a picture of it. This looks stupid. Anyway, it looks like a carrot stuck in. I don't know what the heck this thing is, but maybe I should back off. I don't know what I'm getting at, except that you would want as much mass as possible concentrated right around the axis, and then you want very little mass outside of that. So if you imagine some really super lightweight wheel, but then a bunch of mass packed, sticking out around the axis, this would be the easiest thing to rotate. And the hardest thing to rotate is a really lightweight wheel where you put all the mass right out around the edge, like a gyroscope. Gyroscopes are designed to make it hard to start turning them, and then hard to stop also. So once you do get a gyroscope spinning, it spins a long time. All right, I'm getting kind of distracted. I don't think it's helping. Getting off course. So number 3, how would the results be different if some objects had more mass or greater size? I'm just going to tell you, it doesn't matter. Just like an object falling can have a lot of mass or a little mass, all objects fall at the same rate if you neglect friction. So it's the same with these kinds of things. You could have a big sphere and a little sphere, and as long as they have the same mass distribution, same density, same shape, they're going to roll at the same speed. Same with hoops. Very last one, what would happen if this were frictionless? No friction in the ramp. I'd like somebody to answer that. What do you think would happen if we got rid of all the friction? Which one would get to the bottom first? Well, how would things be different? Max, are you raising your hand, or is it still up from an earlier time?
It's still up, but I think I know the answer.
What do you think?
They would all be the same, right?
Yes, they would all be just like that box. So none of them would rotate. The only thing that causes these to rotate is the friction underneath them. If you got rid of the friction, the ball could just slide down the hill without the hill ever catching the bottom of it and causing it to kind of go end over end. So they'd all go just as fast as the frictionless box. So today there's a little bit of new stuff and a very short homework assignment. Tomorrow maybe a little bit more. But first, if anybody had any questions about the homework, this is the time to ask those. So here's the key to Mr. Pennington's questions, the kinematics of rotation practice. Do anybody have any questions about any of the problems there? Or just number 1 and then 2 parts of number 2? Going once, going twice, gone. All right. So this new thing is, I've got to find my notes. I'm going to dig out my packet. It's just the next page of the packet, and it's rotational dynamics, I think is what it's called in the packet. I'm hoping I can find it. All right, this will work. This is my packet for the other class, but the other class I couldn't find my packet, so I used a blank one. All right, rotational inertia. Kind of a complicated issue, and maybe a little odd, especially because there are all these weird formulas that are down here, and the diagrams look very complex. These formulas, mr squared, 1/2 mr squared plus 1/12 mw squared, it seems very complicated, but I think it'll be okay in the end. might be a little fuzzy for a while. To sum up what this is, I'm not sure why it's called dynamics, but this is all about the equivalent of mass. So as I've told you before, force is kind of like torque. And angular acceleration is like linear acceleration. There are all these similar things, but today we're going to get to the angular equivalent of mass. And the angular equivalent of mass is this quantity called I, or moment of inertia, or rotational inertia. And so that's the point of all this. There's some practices on the back that aren't too bad. So Mr. Pennington starts out by trying to give the example of a door, and it's a good way to think about some of the factors that are involved. I'm going to close the door. There's somebody talking and giggling in the other room. So I'm going to draw this door, and then I'm going to talk about what he's saying. So here's a door that's open, partially open to our left. This is the doorway. Here's the floor. So it looks like a real room. There. All right. So that's the door. This says a door opens more slowly if you push it closer to its hinges. So if the door is almost open anyway, but if you wanted to continue opening it, you could push it right here. The hinges would be, maybe there's one hinge and then another hinge down here. So if you push it here and you push it there, and assuming that you use the same force in both cases, it's going to open more slowly pushing it close to the hinge. And it's going to open more quickly pushing it farther from the hinge. Here you get more torque, and here you have less torque. The door will also open more slowly if it's more massive. So if this were a plastic door, a little force right here might open it pretty quickly, and a little force right here might open it really quickly. But if we made it thicker and made it out of concrete, then you could use those same forces, and it's going to open really slowly if you push here, and it's going to open faster here, but still slowly. And to go on a little bit with what I was talking about with the hoops and the wheels and things like that, imagine a door where I cut a big hole over here. Actually, no, I'm going to cut a hole on the other side, dividing the door down the middle, and then I cut a big hole on the side far from the hinges. So this is just all open space. And then I push. That's going to make this door easier to open. If I concentrate all the weight close to the hinges and I have less weight farther from the hinges, it's going to be pretty easy to open. But if I reshuffled the weight of the door, had it open on this side, and then put all the weight out here, that's going to make it harder to open. So this is just to show how force and acceleration in this case of the door are related, and also it's more complicated than our original relationship between, say, force acting on this box and acceleration of this box. So if you apply a force here, then the box is going to accelerate that way. Because it didn't really matter where the force was applied on the box, but with rotating stuff it does. You get different amounts of torque if you apply the force in different places. So let me just fill this in now. The door opens more slowly if you push it closer to its hinges. The door will also open more slowly if it's massive. From a torque and angular acceleration perspective, the blank the applied force and the blank it is applied from the pivot point, the greater the acceleration. So the greater the applied force, like if I applied a bigger force here and a bigger force there, we would get a greater acceleration. And the farther it is applied from the pivot point, the greater the acceleration. So there are two ways to make this door accelerate open more quickly. One is to apply a big force, and the other is to apply the force as far away from the hinges as you can. The angular acceleration is blank proportional to mass. So to figure that one out, if we think about how fast this door is going to accelerate, will I be able to accelerate it open more if it has a big mass or a small mass? And the answer is a lower mass gives me bigger acceleration. So it's inversely. These relationships are analogous to the familiar relationships of force, mass, and acceleration. So in the case of this box down here, we used to do net force equals ma, which means if I apply the same net force and I have a very massive box, then I'm going to get a small acceleration. And if I apply the same net force and I have a really small box, a low mass box, then I get a big acceleration. And it's the same with the door, but with the further complication that depends on where you apply the force. Number 2, so starting with Newton's second law, derive an expression for torque in terms of mass, lever arm R, and angular acceleration alpha, and introduce I, rotational inertia or moment of inertia. So this is the equivalent. This is like the new M. This is the new mass. And basically, I'm going to take Newton's second law, which is F equals ma, and we're going to get the new rotational Newton's second law from that. So, first step, you'll never have to reproduce this. This is just showing you how the sausage is made, although it's not really that disgusting. So torque equals Fr. We've been over that one before. That's force times lever arm. People seem good with that. And I'm just going to go down and write that again, but then I'm going to do a substitution. So torque equals Fr, but I'm going to combine that with F equals ma. I'm not going to use the summation symbol and write F net, but F equals ma. This is Newton's second law. And if F equals ma, then I can put in ma for F. So torque equals a force that's applied times a lever arm. I'm just going to say torque equals mass times acceleration times a lever arm. So these two things are equal. And I want to make this an entirely rotational expression. And I've got this linear acceleration in here. So if I remember that linear acceleration equals angular acceleration times r, now I can substitute in alpha r for this. So torque equals m times alpha r times r. And that can be written as torque equals mr squared. You can write it different ways, but it's convenient if I write mr squared times alpha. And this part right here, the mr squared, that is, we're going to give that a new name and call that I, which is moment of inertia or rotational inertia. So I equals mr squared. And on this next line, this is just formalizing kind of what's been done here. So Newton's second law is F equals ma. That's Newton's second law for linear motion. And Newton's second law for rotational motion is torque equals I alpha. And the analogous things in there, instead of force, now we have the rotational analog of force, which is torque. Torque is sort of a twisting force. And instead of mass, we have the new rotational analog of mass, which is this thing called moment of inertia, which all these are just formulas for moments of inertia for different types of objects. And this tells you how hard it is to get something moving or stop a moving object in a straight line. This tells you how hard it is to begin rotating something or stop something's rotation. And then finally, A, which is linear acceleration, is the equivalent of angular acceleration. So it's the same thing. That's what we're doing. We're going through, as we go through this unit, we're coming up with new rotational versions of everything we had in kinematics and Newton's laws, basically. So now we have two definitions of torque. One is the one that we started the unit with. Torque equals force times radius, or force times lever arm. And then this new one is torque equals I alpha, which allows us to do a lot more things. Now we can use these two formulas. We could say FR equals I alpha and do lots of stuff now. So these mysterious moments of inertia over here, they are, so if you want to apply this formula to a thin hoop, you would plug in mr squared for I. If you wanted to apply this formula to a solid cylinder, you would plug in 1/2 mr squared for I. If you wanted to do this for a sphere, it's 2/5 mr squared you plug in for I. And what I'm about to do here is explain where these come from. You won't ever be expected to derive these. You could just come up with them. You will be expected to know this, a single, like the rotational inertia of a single point mass. You need to have that memorized because that's fundamental. So here's what I mean by a single point mass. If you picture a stick, this is the axis of rotation, and there's rotation around the stick like that, and you have a mass that's off-centered this far, and that distance from the center of mass really to the center of rotation is r. Then, as I showed up here, I is going to be mr squared. So for a single point mass, I equals mr squared. In fact, for every mass, I equals mr squared. But these points of mass are distributed differently around the solid cylinder than they are around the sphere. You know, the way their radii are very different here on average than their radii are there. This has got a lot of them that are close to the center with smaller radii. This has got a lot of them farther from the center with bigger radii. So when you end up adding all these things up, you're going to get a different value in the end. So for multiple point masses, which all of these are on the right, this is what somebody has done using calculus or using a computer. They have figured out a shortcut. Instead of having to add up every single point of mass on this sphere, you just use this formula. Somebody's done this work for us. So if you have multiple masses, let's say you've got a mass here, and you've got a mass over here, and you've got another mass right here. You basically do the same thing that you do with a single one, but you add them all up. So it's just the summation, or sorry, I should write I equals the summation of mr squared. And again, this is what people have done. They've used this process to come up with those, and you won't have to do that. You can just look it up. But you should know that for a single point of mass, the moment of inertia is mr squared. It's not too much to memorize. So I want to do one example on the back and then point out a couple of other things, and the homework will go pretty quickly. It says to calculate the rotational inertia of a solid sphere of mass 5 kilograms and radius 0.25 meters. So it's a sphere, and it's a solid sphere. That's important because a hollow sphere might be different. This doesn't have hollow spheres on it, but according to our table, it's 2/5 mr squared. You can Google moment of inertia of a spherical shell to see what that is, and it wouldn't be 2/5 mr squared. It'd be something bigger because the mass would be mostly distributed far out from the center. So 2/5 mr squared is what I need. That's my formula. And I can just plug in the values. 2/5 times the mass, which is 5 kilograms. That's kind of convenient. Times the radius squared, 0.25 meters squared. So this is going to be 2, and I think that's 0.625 or 0.0625. Do it anyway. 0.25 squared, 0.0625, and then 2/5 times 5 is just 2. So it's 0.125. And I just realized at this point, and I realized last class, I didn't go over what the units are. So the units, 5 kilograms times meters squared. Kilograms, meters squared. Don't try to even think about what a kilogram meter squared means. It's just kind of nonsense, but those are the units. So number 4 is just, you do exactly the same thing I did, but you just have to look up the moment of inertia of a solid cylinder. Number 5, I think I should warn you a little bit about, especially when you get to C. So number 5, you've got to use this new idea of moment of inertia and torque equals I alpha. So you're going to need this formula, which is like F equals ma for rotating things. And you're going to have to apply it to this grindstone. So you've got a grindstone which has 0.28 meters of radius. And it says there's 180 Newton force tangential to that. So somebody is pushing on it like this with a force of 280 newtons right there. Just basically applying a force right at the end of that lever arm. The mass of this is 75 kilograms. So what torque is exerted, you'll have no problem. Remember that there's the other formula for torque for that one. Angular acceleration, you'll now be able to get that because you know that not only is torque equal to Fr, but it's equal to I times the angular acceleration. And you know that this is a solid disc grindstone. People usually get a little confused when they get to part C, which says, what's the angular acceleration if there's opposing frictional force of 20 newtons, 1.5 centimeters from the axis? So that means not only is there a push this way, but at the distance of 1.5 centimeters from the axis, there would be this opposing force. So this would, I'm drawing this as a counterclockwise force, sorry, a clockwise force. Then there would be this other counterclockwise force of friction. So you'll need to, when you're thinking about the torque on this system, this is actually net torque. And just like when we were balancing beams and things, where you have a weight over here and a weight over here, and what we were trying to do is make the net torque equal 0. You can have multiple torques that add up to the total torque. So in this case, you're going to have 2 torques. I won't say anything more. I think you can figure it out. Look at Mr. Pennington's solutions if you need to. Check your answers as you go. Any questions from anybody?